Well, pre-calculus classes, good morning, good afternoon, or good evening. We will go ahead and finish up the discussion of section 2.3 here with this set of notes. And certainly, again, I think you'll see some review concepts from last year. You may see some new information as we solve and find zeros of polynomials as well. So, if you have a polynomial function f of degree n, the graph of f has at most n minus 1 turning points. What that means is, if you think about a parabola, x squared. Well, a parabola has one turning point. If you have a cubic function, at most it will have two turning points. Now, it doesn't have to have that amount, but it will have at most n minus 1. The function f has at most n real zeros. So, whatever the degree is usually an indicator of how many zeros a function has. And we'll even talk here in a moment, this term zeros, what that represents as well. When we talk about real zeros of polynomial functions, there are a lot of statements that basically all mean the same thing. X equals a is a zero of a function. X equals a is a solution of the polynomial equation at f of x equals 0. So, whether you see the term zero, solution, if x equals a is a zero or solution, that means x minus a is a factor of the polynomial. A comma 0 is an x-intercept of the graph of x, or of f of x. And then the final term that's kind of interchangeable, x equals a is a root of the function. So certainly you may hear me use the term zero, solution, or root. Those three things are all interchangeable. X-intercepts technically are, although there you are referring to an ordered pair, but these three things are truly interchangeable. If you even want to argue x-intercepts means there are 4 interchangeable terms, that's okay as well. Alright, so kind of talking a little bit about some things that we've either just addressed in these notes, things from what we've already talked about. How many turning points could be on the graph? Well, there could be up to, if the degree is 4, up to 3 turning points. Now, as far as the end behavior goes, and this is where we'll even give you another abbreviation here in a couple of moments, but as far as the end behavior goes, the degree is 4, which again, what we care about is that it's even. The leading coefficient is -2. Again, what we really care about is that it's negative. So, from there, as x approaches negative infinity, as x approaches positive infinity, well, things we've already discussed. Because it's even, they are both y-n behaviors are either going to go up or down. It's even and negative, well, both y-n behaviors will go downward. So, there is that, which again reviews over what we talked about in the first half of 2.3. Now, factor and give the zeros. Well, if we have -2x to the 4th plus 2x squared, well, as far as factoring goes, there is a GCF, -2x squared. If we take -2x squared out, we end up with x squared minus 1, and then that factors into x plus 1 and x minus 1. So these zeros are positive and -1. And then the -2x squared, if you want to set that equal to 0, divide and take the square root. Well, since that's just 0, Square root of 0 is 0. Now, as far as a sketch, we're going to do a very rough sketch here. Our zeros occur at 1, 0, and -1. Now, I always kind of liken this to, we're essentially going to put together a puzzle here. We're going to use the zeros where it goes through or touches the axis and the end behavior. Now, what the end behavior tells us, at this last 0 at +1, because the end behavior is going to -infinity, our graph is going to be pointing down. We also know at -1, our graph is going to be pointing down. There is no way the graph can turn and go back up. Otherwise, we would have found a 0 somewhere either out here or out here. Now, the other thing, we know the graph is somewhere between -1 and 0, going to go up and come down to 0. Now, I can't do anything else from here just yet. We also know somewhere the graph's going to go up, come back down. Now, here is where we know the graph cannot ever cross back through, go up through the 0. So, and we're even going to talk in a moment about kind of why I knew that it's going to form a turning point right there. But again, if it were to cross either here to go back up or here to go back up, well, again, you would have found an additional 0. It cannot cross back over the axis. So, again, let's look at what we have. Up to 3 turning points. Well, 1, 2, 3. If it's 4th degree, you can't have more than 3. And behavior we found, and then we found our 3 zeros. There could have been up to 4. Usually if it's x to the 4th, there will be 4. We're going to talk about why there were only 3 here in just a moment. Now, the reason why this one not only doesn't cross, but also has 1 fewer zeros than the degree is this -2x squared. It is a repeated 0. A factor x minus a to the k, where k is greater than 1, yields a repeated 0 with a term of what we call a multiplicity of k. Again, hopefully that's a term you at least heard a little bit of last year. If k is odd, the graph crosses the x-axis. If k is even, the graph bounces off the x-axis but does not cross it. You may have had teachers in the past that say the graph touches the x-axis, doesn't cross it. I've coached enough sports over the years, I probably have just gotten used to saying it bounces. So you can see it bounces off the x-axis right there. So we will talk more about not only these two things, but certain other things as well. All right, so graphing a polynomial function. We're going to use the LCT, or the LC test, or again, the LCT, which is the leading coefficient test to determine end behavior. We'll always talk about the possible number of turning points, find x-intercepts and multiplicities. We'll find the y-intercept. I know we talked about that in, I think, section 2.2. And then you may have to plot some additional points. You know, unlike this rough sketch, you know, we will at least talk about a way to maybe roughly identify where that turning point is. And so we want at least 1 point before and after each 0, between them, sometimes the before and after we'll discuss whether or not that would really be needed. You sometimes can use symmetry as well. So, f of x equals 3x to the 4th minus 4x to the 3rd. All right, first off, the leading coefficient test. Well, the degree is even. The leading coefficient is positive. From now on, I'm not even going to worry about what the numbers are. All we really care about is it's even and positive. So that means as x approaches negative infinity and positive infinity, well, again, because it's even, both y characteristics will be the same. It's even and positive. Both y's will approach positive infinity. It's 4th degree, so up to 3 turning points. Next up, x-intercepts. Well, we'll factor. So 3x to the 4th minus 4x to the 3rd. Factor out x to the 3rd as my GCF. So 3x minus 4. So our zeros are x equals 4/3, and if you take the 3rd root of 0, x is also 0. So what we can do is plot those. Now, from here, what we can also do, find the y-intercept. Whether or not you remember to find the y-intercept, plug 0 in for x. Well, if I put 0 in for x, those actually just are 3 times 0 minus 4 times 0, so the y-intercept is also 0. One thing that we'll certainly talk about as we go, if the x-intercept is 0, the y-intercept will also be 0 because it's at 0, 0. So the y-intercept may not help us always. Now, some additional points. We know the graph is going to go up to positive infinity there and there. Now, from here, and this is one of the reasons why I would say, use pencil over pen. I just know that, especially if we're creating videos, the pen shows up a little better for you guys. Now, plotting some extra points. The only one you really need here, you could plug in positive 2, negative 1, just to reaffirm your end behavior. With end behavior, you don't really need points after. We do need a value in between 0 and 4/3. Because we have to, we want to at least try to, add in a little more accurate detail to this. So, again, you can use anything you want between 0 and 4/3. Well, the only real convenient value is 1. So if I plug 1 in for x, I get 3 minus 4, negative 1. So what we know is there is going to be a turning point there. So our graph, again, because it's odd, at x to the 3rd. Now, this x equals 0 does have a multiplicity of 3. It still goes through. So I'm going to try to at least somewhat get rid of that. So you can see there that one is a, still fairly rough sketch, but we do at least add in a little bit of detail as to where does that turning point occur. All right, one final example. Sketch the graph of f of x equals negative 2x to the 3rd plus 6x squared minus 9 halves x. If you want, certainly we'll include kind of the guidelines for graphing again for our LCT degree is odd. Leading coefficient is negative. So, as x approaches negative and positive infinity, well, when it is odd and negative, the y values are opposite of x. So as x goes down, y goes up. As x goes up, y goes down to negative infinity. There can be up to 2 turning points. Now our x-intercepts. Well, first thing that I am going to do to actually make this a little bit easier, because when I see this, the first thing I do not like at all is the fraction. I'm going to factor out not only a half, but actually negative a half and x. Now, if I factor negative a half out of negative 2, it leaves 4x squared. Divide 6 by negative a half, 12x, and divide negative a half out of that. It's going to leave me with positive 9. This actually works out kind of nicely from here. If you happen to see this, what multiplies to 36 adds to 12? Well, because these are the same, it's going to be 2x plus 3 and 2x plus 3. The reason you can split the middle, if you see these are the same, that means it's going to be either a sum or difference of squares. Well, 2 times 2 is the 4x squared. 3 times 3 gives me the 9, and then the negative 1/2 x. So our zeros are x and negative 3/2 with a multiplicity of 2. Once again, if you want to split the middle to do that, you will end up with the same thing. But when you see multiplies to 36 adds to 12, because these are the same, it is going to be a square. Now, your y-intercept, plug 0 in for x. Well, if you plug 0 in for all of the x's, it's also 0, which again, anytime the x-intercept is 0, your y-intercept will be as well. So, a couple of key things here. We know it is going to bounce at negative 3/2. Now, we also know to the right, y is going down. So at this 0, it is going to be going down. At this 0, we know it's going to go up, and we also know it is going to have a bounce. The last thing that we are going to need to do is plug in a value in between 0 and negative 3/2. I'll use negative 1. When you plug negative 1 in, that is, let's see here, positive 2, positive 6, negative 3/2, or 9/2. So positive 2, positive 6 is 8, minus 4.5. Or here we can even do 8 minus 9/2. 3.5. If you want to, press math, convert it to a fraction. 7/2. So that is going to put my graph there. Again, multiplicity of 2, we know it is going to bounce, come back down, and go through the 0. So again, you're kind of, like I like to say, using leading coefficient test and behavior, the zeros, possibly the y-intercept, maybe an extra point here or there, to put together the puzzle. All right, final things in 2.3. Sometimes we're going to have you work backwards. Find a polynomial of degree n that has the given zeros. Degree is 2, a 0 at -3. Well, here we're basically working backwards. I always like to say, think of it as we're telling you x equals -3. Go backwards. We are going to create the polynomial from the factors. If x equals -3, it has a factor at x plus 3. Now, we've said the degree is 2. Well, in theory, there should be 2 zeros, but if they've only told us there is a 0 at -3, this is squared. So that is, again, because it's polynomial, either f of x equals y equals, we'll kind of leave that up to you. All right, zeros at 0, -1, and 2. So again, we're saying x is 0, x is -1, x is 2. So from here, x plus 1, x minus 2. And then all that is left is f of x equals, now because it's degree of 4, one of these has a multiplicity. You could put the square here, here, or here. Doesn't matter. I'm just going to put it with the x squared since they haven't told us which one specifically. All right, one final question. Here, x equals -6, n is 2, passes through -5, -2. This is something you haven't seen yet. Well, that tells us y equals x plus 6, because the degree is 2 squared. If they tell you it passes through a point, that means there's going to be a leading coefficient other than 1. To find that a value, you plug these numbers back in. This is x, this is y. So -2 equals a, -5 plus 6 squared. Well, when we do that, -2 equals -5 plus 6 is 1 squared. So a is -2. So y equals -2x plus 6 squared. So again, anytime they tell you it passes through a point, that does mean you are going to have to find a leading coefficient for a. So I know the second half of 2.3 a little bit longer set of notes, but that does complete everything from this section.